Good day and welcome back to our second and final installment on velocity and acceleration. This is the part of the discussion where we are going to focus in and have a little bit of fun with the acceleration vector. But to get us started, I want to recall a concept from our previous section. We defined the unit tangent vector to be r prime divided by its length. But for us in this section, we are thinking of r as representing a position function. So r prime would really represent velocity. And if we are dividing by the magnitude of velocity, that is really speed. So I'm going to go ahead and introduce some notation. Speed is a scalar quantity. That is, we're taking the magnitude of a vector. So let's introduce the name gamma of t. So the unit tangent vector we can think of as being velocity over speed. And just to make sure we're kind of all on the same page as we go along, when we see this later on, I just want to note gamma of t is the magnitude of velocity, which is the magnitude of r prime. And if you were to equate the unit tangent vector with this alternative representation of it, you could solve for the velocity vector by multiplying both sides by that speed, gamma. That is, velocity is really equal to gamma times the unit tangent vector. And this really provides us with a nice starting point to talk about acceleration. The reason being, velocity, when you differentiate it, gives you acceleration. So to get a representation for acceleration, what we are going to do is differentiate our velocity formula. And when we do so, we need to use one of our product rules. It tells us we take the derivative of the first times the second plus the first multiplied by the derivative of the second. And this is a spot where I can pause for a moment and maybe give you a little bit of intuition as to what we are working towards. And what we would like to do is take acceleration and break it down into what we call its tangential and normal components. That is, we want to have some quantity times the unit tangent vector, which we have, plus some other quantity involving the unit normal vector. And I also want to throw out there maybe a disclaimer in a sense. I will not ask you to recreate these calculations or computations at any point, but I do think they involve some really good ideas related to our previous material, so it's certainly worth us spending a few minutes to kind of generate this out. Now, to get the unit normal vector to come into play, let me remind you how we define the unit normal vector. The unit normal is the tangent prime divided by its magnitude. So what I would like to do is kind of cut and paste down. So the first part is going to remain exactly the same. And then for the second part, I'm going to leave a little bit of space, and you will see why. Somehow I want to get that unit normal to come into the picture. And if I want this to be the unit normal, I need to divide t prime by its magnitude. But remember, I can't just multiply by this scalar for free. We have to balance it, in a sense. So we'll go ahead and throw that in the top as well. All right, so just manipulating it to become exactly what we want it to become. So we have gamma prime times the unit tangent, plus we have gamma of t times the magnitude of t prime. And I'm going to leave a little bit of space again here, just for fun, multiplied by the unit normal vector. So this is precisely what we said we are shooting for. We want to take the acceleration vector and break it down into a quantity involving the unit tangent and another quantity involving the unit normal. And what I would like to do is make sure that I have kind of nice, convenient formulas to work with for the portions of that acceleration vector in front of each of these. So in order to make this, I don't know, maybe kind of as nice as possible, I'm going to remind you of another formula from our previous section. A representation for curvature is the magnitude of t prime divided by the magnitude of r prime. And with that in mind, we'll go ahead and turn this magnitude of t prime into curvature. And if I would like to turn that into curvature, I need to divide by, well, what we might think of as speed, and I need to multiply by that same quantity. But note that what we are multiplying by is really just gamma of t. So if I do one last kind of little simplification, the first part is still remaining exactly the same. I can write this second part as gamma squared multiplied by the curvature times the unit normal vector. And what we've done is we've now taken the acceleration and we've broken it up into what we're going to think of as its tangential and normal components. So let me go ahead and summarize this. And now is the part where we need to make sure we are familiar with the following details. So what we've seen is that the acceleration vector can be written exactly in the form that we have above. So some scalar quantity a sub t times the unit tangent plus some scalar quantity, let's say a sub n, times the unit normal vector, where the a sub t is equal to gamma prime of t, and the a sub n is equal to gamma squared times curvature. And depending upon the context that we are working in, we can also write these in slightly more convenient forms. A of t is r prime dotted with r double prime divided by the magnitude of r prime. And a sub n would be the magnitude of r prime crossed with r double prime divided by the magnitude of r prime. And at this point, we could certainly dive into a few details and computations and see where these formulas come from, but I don't think it will necessarily add anything to our conversation. And one of the difficulties is really kind of picking and choosing what details to include, and the above details I think are much more relevant. And with that in mind, let me go ahead and make an observation. So we refer to the a sub t as the tangential component, the a sub n as the normal component of acceleration. And let me just represent this graphically as simply as I can. So assuming we have some kind of space curve, I'm going to call it r of t. And I'm not going to embed it in 3 dimensions. I think that maybe makes the picture a bit more difficult to see. But at a point on the curve, so call this P, we have a unit tangent vector, so kind of going in the direction of the curve, unit length. We also have a unit normal vector, so unit length pointing in a sense inside the motion of the curve. And what our above work tells us is that acceleration is going to lie somewhere in that plane, which is determined by the unit tangent and the unit normal vector. And to follow up, a quick question for you. What do we call that plane determined by the unit tangent and unit normal vector? And if you said the oscillating plane, you are absolutely correct. So let me just finish with a quick note. Acceleration at a point P lies in the oscillating point plane at P. Which finishes up the first part of this video, kind of coming up with this way of viewing the acceleration vector. For the next part of the video, I want to look at one example, just kind of calculating out these quantities, and then finish by giving kind of a physical interpretation that I think we can all relate to. Now for a common example. A particle travels along some space curve. What we would like to do is determine its tangential and normal components of acceleration. So what I would like you to do is pause the video and take, I don't know, maybe 4 or 5 minutes. It's highly computational, and come up with the tangential and normal components of acceleration. And while you do that, I'm going to go ahead and pause my video as well, and I'm going to write everything down on the screen. So I'm going to wait about 10 seconds to do that. And poof, I feel like I need some sound effects. But anyhow, we now have all of the relevant work. In order to find the tangential and the normal components of acceleration, we essentially need 3 building blocks: r prime, r double prime, and speed. And combining everything together, we find that the tangential component of acceleration is going to be 0. And the normal component of acceleration, if you go through the details of the cross product, it becomes the vector sine minus cosine 1, which is very similar to above. Note it also has the same length, the square root of 2. So square root 2 over square root 2 equals 1. And this is a point where I would be asking you a question in class. When the speed of an object is constant, what does that tell you the acceleration is going to be? Typically what happens is I get 3 or 4 people tell me very adamantly the acceleration is going to be 0. And that's not quite true, because there is a normal component to that acceleration. When the speed is constant, the tangential component of acceleration is 0. So let's just make this observation and use this as a wrapping up point for the discussion. So note, if speed is constant, then the tangential component of acceleration is 0. And if one was so inclined, you could certainly kind of explain why this is. If the speed is constant, what you can show is that r prime dotted with r double prime is going to end up being 0. Similar to some computations we did at the end of our second video covering the 13.2 or the calculus of vector valued functions material. Now, in order to kind of make some intuitive sense in a way that we can all relate to, what I would like to do is give you kind of a car analogy. What we want to imagine that we are doing is traveling down a road in a car. And when you're traveling down the road in a car, you're going to feel acceleration in kind of 2 different ways. There's the acceleration you feel when you kind of put the pedal down really hard. It pushes you back in your seat. That would be the tangential component of acceleration. But if you imagine the car kind of going around a curve, what happens is you feel your body shifting to the side. That would be the normal component of acceleration. So if you are traveling down a road at a constant speed and it is a perfectly straight road, your tangential component of acceleration is certainly going to be 0. You don't feel anything pushing you back in that seat. But if you continue on at that constant speed and we encounter a curve, even if it's just a small curve, you will feel that normal component of acceleration. So that completes our video. As usual, I recommend going through completing the suggested problems. If you have questions, do not hesitate to drop me an email or stop by our virtual office hours. So stay tuned and take care.